Wave power is the transport of energy by ocean surface waves, and the capture of that energy to do useful work. For example, electricity generation, water desalination, or the pumping of water. Machinery able to exploit wave power is generally known as a wave energy converter. Wave power is distinct from the diurnal flux of tidal power and the steady gyre of ocean currents. Wave power generation is not currently a widely employed commercial technology, although there have been attempts to use it since at least 1890. In 2008, the first experimental wave farm was opened in Portugal, at the Aguçadoura Wave Park. The major competitor of wave power is offshore wind power. Physical concepts. See energy, power and work for more information on these important physical concepts. See wind wave for more information on ocean waves. Waves are generated by wind passing over the surface of the sea. As long as the waves propagate slower than the wind speed just above the waves, there is an energy transferred from the wind to the waves. Both air pressure differences between the upwind and the lee side of a wave crest, as well as friction on the water surface by the wind, making the water to go into the shear stress causes the growth of the waves. Wave height is determined by wind speed, the duration of time the wind has been blowing, fetch and by the depth and topography of the sea floor. A given wind speed has a matching practical limit over which time or distance will not produce larger waves. When this limit has been reached, a sea is said to be fully developed. In general, larger waves are more powerful, but wave power is also determined by wave speed, wavelength, and water density. Oscillatory motion is highest at the surface and diminishes exponentially with depth. However, for standing waves near a reflecting coast, wave energy is also present as pressure oscillations at great depth, producing microseisms. These pressure fluctuations at greater depth are too small to be interesting from the point of view of wave power. The waves propagate on the ocean's surface, and the wave energy is also transported horizontally with a group velocity. The mean transport rate of the wave energy through a vertical plane of unit width, parallel to a wave crest, is called the wave energy flux. Wave power formula: in deep water where the water depth is larger than half the wavelength, the wave energy flux is with P the wave energy flux per unit of wave crest length, HMO the significant wave height, TE the wave energy period, I the water density and G the acceleration by gravity. The above formula states that wave power is proportional to the wave energy period and to the square of the wave height. When the significant wave height is given in meters, and the wave period in seconds, the result is the wave power in kilowatts per meter of wavefront length. Example: consider moderate ocean swells, in deep water, a few km off a coastline, with a wave height of 3 m and a wave energy period of 8 seconds. Using the formula to solve the power, we get meaning there are 36 kilowatts of power potential per meter of wave crest. In major storms, the largest waves offshore are about 15 meters high and have a period of about 15 seconds. According to the above formula, such waves carry about 1.7 lmW of power across each meter of wavefront. An effective wave power device captures as much as possible of the wave energy flux. As a result, the waves will be of lower height in the region behind the wave power device. Wave energy and wave energy flux: in a sea state, the average, mean, energy density per unit area of gravity waves on the water surface is proportional to the wave height squared, according to linear wave theory. Where E is the mean wave energy density per unit horizontal area, the sum of kinetic and potential energy density per unit horizontal area. The potential energy density is equal to the kinetic energy, both contributing half to the wave energy density E, as can be expected from the equipartition theorem. In ocean waves, surface tension effects are negligible for wavelengths above a few decimeters. As the waves propagate, their energy is transported. The energy transport velocity is the group velocity. As a result, the wave energy flux, through a vertical plane of unit width perpendicular to the wave propagation direction, is equal to with Cg the group velocity. Due to the dispersion relation for water waves under the action of gravity, the group velocity depends on the wavelength I, or equivalently, on the wave period t. Further, the dispersion relation is a function of the water depth h. As a result, the group velocity behaves differently in the limits of deep and shallow water, and at intermediate depths, deep water characteristics and opportunities. Deep water corresponds with a water depth larger than half the wavelength, which is the common situation in the sea and ocean. In deep water, longer period waves propagate faster and transport their energy faster. The deep water group velocity is half the phase velocity. In shallow water, for wavelengths larger than about 20 times the water depth, as found quite often near the coast, the group velocity is equal to the phase velocity. History. The first known patent to use energy from ocean waves dates back to 1799, and was filed in Paris by Girard and his son. An early application of wave power was a device constructed around 1910 by Bochet-Precique to light and power his house at Royan, near Bordeaux in France. It appears that this was the first oscillating water column type of wave energy device. From 1855 to 1973 there were already 340 patents filed in the UK alone. Modern scientific pursuit of wave energy was pioneered by Yoshio Masuda's experiments in the 1940s. He has tested various concepts of wave energy devices at sea, with several hundred units used to power navigation lights. Among these was the concept of extracting power from the angular motion at the joints of an articulated raft, which was proposed in the 1950s by Masuda. A renewed interest in wave energy was motivated by the oil crisis in 1973. A number of university researchers re-examined the potential to generate energy from ocean waves, among whom notably was Stephen Salter from the University of Edinburgh, Kjell Budal and Johannes Falms from Norwegian Institute of Technology, Michael E. McCormick from US Naval Academy, David Evans from Bristol University, Michael French from University of Lancaster, Nick Newman and C.C. Merry from MIT. Stephen Salter's 1974 invention became known as Salter's duck or nodding duck, although it was officially referred to as the Edinburgh duck. In small-scale controlled tests, the duck's curved cam-like body can stop 90% of wave motion and can convert 90% of that to electricity, giving 81% efficiency. In the 1980s, as the oil price went down, wave energy funding was drastically reduced. Nevertheless, a few first-generation prototypes were tested at sea. More recently, following the issue of climate change, there is again a growing interest worldwide for renewable energy, including wave energy. The world's first marine energy test facility was established in 2003 to kickstart the development of a wave and tidal energy industry in the UK. Based in Orkney, Scotland, the European Marine Energy Centre has supported the deployment of more wave and tidal energy devices than at any other single site in the world. EMEC provides a variety of test sites in real sea conditions. Its grid-connected wave test site is situated at Billia-Crewe, on the western edge of the Orkney mainland, and is subject to the full force of the Atlantic Ocean with seas as high as 19 metres recorded at the site. Wave energy developers currently testing at the centre include Aquamarine Power, Polamis Wave Power, Scottish Power Renewables and Wello. Modern technology, wave power devices are generally categorized by the method used to capture the energy of the waves, by location and by the power takeoff system. Locations are shoreline, nearshore and offshore. Types of power takeoff include hydraulic ram, elastomeric hose pump, pump to shore, hydroelectric turbine, air turbine, and linear electrical generator. When evaluating wave energy as a technology type, it is important to distinguish between the four most common approaches: point absorber buoys, surface attenuators, oscillating water columns, and overtopping devices. Point absorber buoy: this device floats on the surface of the water, held in place by cables connected to the seabed. Buoys use the rise and fall of swells to drive hydraulic pumps and generate electricity. EMF generated by electrical transmission cables and acoustic of these devices may be a concern for marine organisms. The presence of the buoys may affect fish, marine mammals, and birds as potential minor collision risk and roosting sites. Potential also exists for entanglement in mooring lines. Energy removed from the waves may also affect the shoreline, resulting in a recommendation that sites remain a considerable distance from the shore. Surface attenuator. These devices act similarly to point absorber buoys, with multiple floating segments connected to one another and are oriented perpendicular to incoming waves. A flexing motion is created by swells that drive hydraulic pumps to generate electricity. Environmental effects are similar to those of point absorber buoys, with an additional concern that organisms could be pinched in the joints. Oscillating water column. Oscillating water column devices can be located on shore or in deeper waters offshore. With an air chamber integrated into the device, swells compress air in the chambers, forcing air through an air turbine to create electricity. Significant noise is produced as air is pushed through the turbines, potentially affecting birds and other marine organisms within the vicinity of the device. There is also concern about marine organisms getting trapped or entangled within the air chambers. Overtopping device. Overtopping devices are long structures that use wave velocity to fill a reservoir to a greater water level than the surrounding ocean. The potential energy in the reservoir height is then captured with low head turbines. Devices can be either onshore or floating offshore. Floating devices will have environmental concerns about the mirroring system affecting benthic organisms, organisms becoming entangled, or EMF effects produced from subsea cables. There is also some concern regarding low levels of turbine noise and wave energy removal affecting the near-field habitat. Oscillating wave surge converter. These devices typically have one end fixed to a structure or the seabed while the other end is free to move. Energy is collected from the relative motion of the body compared to the fixed point. Oscillating wave surge converters often come in the form of floats, flaps, or membranes. Environmental concerns include minor risk of collision, artificial reefing near the fixed point, EMF effects from subsea cables, and energy removal affecting sediment transport. Some of these designs incorporate parabolic reflectors as a means of increasing the wave energy at the point of capture. These capture systems use the rise and fall motion of waves to capture energy. Once the wave energy is captured at a wave source, power must be carried to the point of use or to a connection to the electrical grid by transmission power cables. The table contains descriptions of some wave power systems. A more complete list of wave energy developers is maintained here. Wave energy developers, environmental effects. Common environmental concerns associated with marine energy developments include the risk of marine mammals and fish being struck by tidal turbine blades. The effects of EMF and underwater noise emitted from operating marine energy devices. The physical presence of marine energy projects and their potential to alter the behavior of marine mammals, fish, and seabirds with attraction or avoidance. The potential effect on near-field and far-field marine environment and processes such as sediment transport and water quality. The TETHIS database is an online knowledge management system that provides the marine energy community with access to information and scientific literature on environmental effects of marine energy developments. Potential. The worldwide resource of wave energy has been estimated to be greater than 2 TW. Locations with the most potential for wave power include the western seaboard of Europe, the northern coast of the UK, and the Pacific coastlines of North and South America, Southern Africa, Australia, and New Zealand. The North and South temperate zones have the best sites for capturing wave power. The prevailing westerlies in these zones blow strongest in winter. Challenges. There is a potential impact on the marine environment. Noise pollution, for example, could have negative impact if not monitored, although the noise and visible impact of each design varies greatly. Other biophysical impacts of scaling up the technology is being studied. In terms of socio-economic challenges, wave farms can result in the displacement of commercial and recreational fishermen from productive fishing grounds, can change the pattern of beach sand nourishment, and may represent hazards to safe navigation. Waves generate about 2,700 gigawatts of power. Of those 2,700 gigawatts, only about 500 gigawatts can be captured with the current technology. Wave farms. Portugal, the Aguçadoura Wave Farm was the world's first wave farm. It was located 5 km offshore near Pascal Cubed de Varzim, north of Porto, Portugal. The farm was designed to use 3 pelamis wave energy converters to convert the motion of the ocean surface waves into electricity, totaling to 2.25 MW in total installed capacity. The farm first generated electricity in July 2008 and was officially opened on September 23, 2008, by the Portuguese Minister of Economy. The wave farm was shut down 2 months after the official opening in November 2008 as a result of the financial collapse of Babcock & Brown due to the global economic crisis. The machines were off-site at this time due to technical problems, and although resolved have not returned to site and were subsequently scrapped in 2011 as the technology had moved on to the P2 variant as supplied to E.ON and Scottish Power Renewables. A second phase of the project planned to increase the installed capacity to 21 MW using a further 25 pelamis machines is in doubt following Babcock's financial collapse. United Kingdom, funding for a 3 MW wave farm in Scotland was announced on February 20, 2007, by the Scottish Executive, at a cost of over £4 million, as part of a £13 million funding package for marine power in Scotland. The first of 66 machines was launched in May 2010. A facility known as Wave Hub has been constructed off the north coast of Cornwall, England, to facilitate wave energy development. The Wave Hub will act as giant extension cable, allowing arrays of wave energy generating devices to be connected to the electricity grid. The Wave Hub will initially allow 20 MW of capacity to be connected, with potential expansion to 40 MW. 4 device manufacturers have so far expressed interest in connecting to the Wave Hub. The scientists have calculated that wave energy gathered at Wave Hub will be enough to power up to 7,500 households. The site has the potential to save greenhouse gas emissions of about 300,000 tons of carbon dioxide in the next 25 years. Australian Aceto Wave Farm off the coast of Western Australia has been operating to prove commercial viability and, after preliminary environmental approval, is poised for further development. Ocean Power Technologies is developing a wave farm connected to the grid near Portland, Victoria through a 19 MW wave power station. The project has received an $66.46 million Australian dollars grant from the Federal Government of Australia. Ocean Links will deploy a commercial-scale demonstrator off the coast of South Australia at Port MacDonnell before the end of 2013. This device, the Green Wave, has a rated electrical capacity of 1 MW. This project has been supported by ARENA through the Emerging Renewables Program. The Green Wave device is a bottom-standing gravity structure, that does not require anchoring or seabed preparation and with no moving parts below the surface of the water. United States, Reedsport, Oregon. A commercial wave park on the west coast of the United States located 2.5 miles offshore near Reedsport, Oregon. The first phase of this project is for 10 PB150 power buoys, or 1.5 megawatts. The Reedsport Wave Farm was scheduled for installation spring 2013. Project has ground to a halt because of legal and technical problems, August, 2013. C. http www.oregonnivcomindex/ssf08/Oregon Wave Energy Stalls off HTML, Patents, U.S. Patent 3,928,967 Euro 1974 Apparatus and method of extracting wave energy Euro The original Salters duct patent, U.S. Patent 4,134,023 Euro 1977 Apparatus for use in the extraction of energy from waves on water Euro Salters method for improving duct efficiency, U.S. Patent 6,194,815 Euro 1999 Piezoelectric rotary electrical energy generator, U.S. application 20,040,217,597 AA Euro 2004 Wave energy converters utilizing pressure differences, see also, Ocean thermal energy conversion, World energy resources and consumption, notes. References. Further reading, Cruz, J. Ocean wave energy Euro current status and future prospects. Springer. ISBN A3-540-74894-6 431 pp. Founds, Johannes. Ocean Waves and Oscillating Systems. Cambridge University Press. ISBN A0-521-01749-1, 288 pp. McCormick, Michael. Ocean Wave Energy Conversion. Dover. ISBN A0-486-46245-5, 256 pp. Tweddell, John. Weir, Anthony D. Weir, Tony. Renewable Energy Resources. Taylor and Francis. ISBN A0-419-25330-0, 601 pp. External links. Wave Energy Converters, a list of main types of wave energy converters, including animations. Wave Energy Developers, Ocean Waves, a new electricity supplier, archived January 7, 2010 at the Wayback Machine, Kate Galbraith. Power from the Restless Sea Stirs the Imagination. New York Times. Retrieved October 9, 2008. Wave Power, The Coming Wave from The Economist, June 5, 2008. Russian company develops mobile wave energy generator. The untimely death of Salter's duck. Ocean power fights current thinking. Wave energy in New Zealand. Wave technologies, types of devices, how it works. Wave power station, environmental effects of renewable energy from the sea tethers.